Julia.
Yes, thanks very much for the introduction. Yeah, welcome to my talk about semi-competitive differential hybrid games. Now, first, for the motivation of all this, why are we doing this? So, cyber-physical systems like trains, planes, autonomous cars, or robots are usually not alone in there.
You're not using the microphone for the whole anyway. You can just speak up a bit. And
Okay,
will
it's
go
fine.
away.
Okay. Those cyber-physical systems are usually not alone in their environment. Autonomous cars, for example, drive in traffic, obviously. Airplanes interact with each other in air traffic, and also robots are usually not alone when they're, for example, working in a crowded warehouse with a lot of other robots. So to ensure the safety of all these systems, it's not enough to alone ensure one single system, but you also have to verify the system's interactions to ensure the safety of the whole. Now, what is usually done to do this is that most of the time, we just look at two players because that's the easiest and smallest situation we can have, and we assume that these players are adversarial. This means one player, so the blue robot here has a goal, and the red robot over there just has the goal that he tries to hinder the blue robot at achieving its goal. So in this scenario, we can pretty easily see that the situation is not safe because, of course, the red robot has a direct option to crash our blue robot. But in reality, that is not usually the case. Usually, the other robot has its own goal too. So, for example, we might know that the red robot actually wants to go over there. So now we can see that the situation is actually safe because we know the red robot tries to reach its goal, so it won't go forward to crash our blue robot. And that kind of situations is what semi-competitive differential game logic can handle. So situations where all of the players have a goal. Now, first, for the structure of my talk, I will first explain in a bit more detail what semi-competitiveness actually is. Then I will talk about the syntax of the logic and also briefly go over the semantics. Then I'll present the proof calculus for the logic, and then there will be a short summary. Now, what is semi-competitiveness? Semi-competitiveness means that the players help each other where it's helpful for them, so they cooperate, or they compete if it's necessary for them. This means, for example, if a player has multiple options which they can choose to win, they will choose one that helps the other player win too. On the other side, player will also not lose on purpose, so if there's only one specific option for them to win, they will not try helping the other player out. This kind of behavior ensures the greatest most cooperation amongst the players, which also ensures monotonicity. Monotonicity means that if we increase the goal, so make it bigger, we then will also have more chances for the player to win. In our logic, the players are called angel and demon. And yes, so monotonicity basically ensures that the logic behaves as expected from it. Now, the interactions between our two players, angel and demon, are described using hybrid games. Those hybrid games can be built up of several connectives. For example, here we have the assignment game, which just assigns a term to a variable. So that is one discrete action. But we can also have continuous actions like the continuous game, where we evolve a variable x according to a differential equation. So this means that time is flowing, and over time the value of x changes according to the differential equation. And at some point, Angel, our first player, says stop, and we stop the time, and then x has a new value. The next game that we have is the test game. Here we test if Angel fulfills the formula Q. So if Q is true, nothing happens. And otherwise, if it's not true, then Angel is going to lose immediately. We also have the choice game where Angel can choose between alpha and beta. And we have the sequential game where we play alpha and then we play beta. The repetition game is some kind of loop, so after each round of game alpha, Angel decides whether she wants to play another round or whether she wants to stop playing. Now, we've heard a lot about Angel, but the game would be really boring if Demon wouldn't have anything to do, so we have the dual game, which switches the controls in game alpha, so everything under Angel's control is now under Demon's control, but also vice versa. That dual game is actually very practical because now we don't have to define all of these games again, but just under Demon's control. So we can save a bit notation effort with this. The actual DGLSC formulas mostly consist of first-order logic formulas with real arithmetic. And also, we of course want to state something about the games that we can play and probably win or not. So we have these modalities here. The first one says that Angel can win the game alpha with her goal P, so she tries to achieve her goal P in the end. And she also knows that Demon's goal is Q. For Demon, it's similar, so we have a modality that states that Demon can win while knowing that Angel's goal is P and he tries to achieve his goal Q. So the information on the other player's goal here is actually pretty important because now with this knowledge we can make assumptions about how the players will behave and what they will probably not do. Now to get those syntax formulas a bit more practical and to give a little example, we here have a small example formula. In this formula, we have Angel and Demon, and both of them are very thirsty. But the problem is their glasses are also very empty. That is signified by the O is 0 and T is 0. So O is the amount in Angel's glass, O because she wants to drink orange juice. T is the amount in Demon's glass because he wants to drink tomato juice. And then there's another problem. Demon has the orange juice bottle and Angel has the tomato juice bottle. So they need to pour drinks for each other. So first it's Angel's turn to pour Demon some tomato juice. This is, you can see with this differential equation here. So while Angel is pouring, the amount of tomato juice in Demon's glass is rising continuously. And after that, it's Demon's turn. So he pours orange juice into Angel's glass. So also here, the amount of orange juice in Angel's glass is rising continuously. And in the end, Angel wants to have the amount 3 of orange juice in her glass, and Demon wants to have the amount 5 of tomato juice in his glass. And now the angle brackets here mean that we're asking if Angel can win the game. So if we imagine this as an adversarial game, it's pretty obvious that we cannot win this game because we don't have control over the variable that matters, for example, for Angel's goal, but also Demon has no control about the variable that matters for his goal. But with semi-competitive behavior, we can say that both of them are able to win the game because they are working semi-competitively. Angel will help Demon achieve his goal, but in turn, Demon will also help Angel achieve her goal. So in this case, we can actually win the game. Now, how do we actually know and define which of the formulas are true and which are not? In the semantics, we define which formulas are true and which not with sets of states. So we have for each formula a set of states where it is true. A state for us is a mapping from the variables to the real values. So in each state, each variable has a distinct value. For first order logic, that's just as we're used to. And for the modalities, we define special functions that we call winning regions that basically backtrack from which states we have to start playing the game so that we can win in the end. So for Angel, this formula is sigma, and for Demon's modality, the formula is delta. And in this little indice here, we always see which game we're playing at the moment, and the X and Y are Angel's and Demon's goal. So for a little example how this actually works, we here have the semantics for the choice game. For Angel, this is pretty straightforward. Angel can choose which game she wants to play, so she can win if she can either win game alpha or if she can win beta. Here in the picture, we can see this with the union of these blue sets. So blue is always Angel's winning region, yellow is Demon's winning region. And we can see here that the winning region for the choice game is just the union of both of the game's winning regions. For Demon, it's a bit more complicated because he can't decide in the game. So for the safe option, he can just say, I can win both of the games. I don't care which game Angel chooses. That is the safe option. But he also knows Angel's goal. He can make some predictions about how she will behave, and she knows that she behaves semi-competitively. So if Demon can win game alpha and he knows Angel can win game alpha too, then he knows that he can also win the choice game because he knows because of Angel's semi-competitiveness, because Angel behaves semi-competitively, she will try to help him and therefore choose alpha. The same goes for game beta. So if Demon can win game beta and Angel can win game beta, he knows that she behaves semi-competitively and will choose exactly this game. Now for a bit more complicated example, this is for the repetition game. Here the problem for the definition is that we don't know beforehand how many rounds Angel wants to play because she can decide after each round and she doesn't have to declare upfront how many rounds she wants to play. So we resort to the usual solution of this kind of problem. We're using fixed points. And there's another little problem. So we always have the goal of the other player there in the winning region definitions too. So what we actually naturally want is to put the other player's fixed point in that, which results in nested fixed points, and that's hard to treat. So we don't do this. We do instead a case distinction. We say either we're playing against the other player, then their fixed point will be the opposite of ours, which is here, this first fixed point for Angel. So here she wants to be in her goal X now or after one more round. Or we say in the second case, we're working together with the other player. So to make the other player happy too, we need to reach the intersection of the goals. But we can then count that the other player has the same fixed point as Angel as well. For Demon, this is pretty similar. So here, that is the case where Demon plays against Angel. So to win the game, he has to be in his goal now and after one more round. The second part of the fixed point is identical with the second part of Angel's definition because, of course, here they're both working together, so they're winning at the same time. So before I start with the important properties of this logic, I would like to do a small excursion to DGL, which is the logic DGLC is based on, and to better understand the properties, I will give a short intro to that logic. DGL is also a logic for reasoning about two-player hybrid games, but it assumes adversarial players. That means more precisely that the goals of the players are opposing. So if Angel has goal P, then Demon's goal will be the complement of P. The syntax of DGL is mostly similar to DGLC, but we don't need both of these goals in the modality because one is clear from the other. So in DGL, we only have one goal here. For daemon, it's the same. So here we only give daemon's goal. One important property of DGL is its determinacy. So that means that either angel can win the game or daemon can win the game, of course, because their goals are opposing. What will also be of importance later is that it has a sound and relative complete proof calculus, and we will use that in a proof later. Now for the properties that I announced. As I already mentioned, the logic is monotone, so if we increase the goal, we also get a bigger winning region, we have more chances to win. And if the goals are complementary or opposing, then the players will behave adversarially, just like in DGL, which makes total sense because in this case, both logics describe the same situation and player behavior. And so the logic is, in this case, defined in a reasonable way. But we cannot only reduce DGLSC to DGL in this special case, but we can in all cases. So if we have any winning region in DGLSC here, for example, for alpha, then we can split it up into DGL winning regions. So the first one is the cooperation case. So the -D here means that we remove all dual games from alpha and give the full control to Angel, but she has to achieve both of the goals at the same time. Or we can decide to try and win the game by competition, so we're playing against the fully adversarial daemon. So now we can either win by cooperation or by competition, which is exactly what semi-competitiveness means. The same also goes for daemon, so we can do the same split up here. That is actually not very clear from the semantics from the start, that you can directly at the start of your game decide whether you want to compete or whether you want to cooperate. Okay, so we also have a proof calculus for this logic, which I will go briefly over. It consists of 5 main parts. So the first are the axioms for Angel. There is 1 per connective. And as well for daemon, we have 1 per connective. Then we have 2 proof rules that state the monotonicity of the logic, and 1 axiom that says that we have determinacy in the case that the goals are opposing. And last but not least, we also have all first order logic rules, which are not listed here. Now, I also have a little example to look at. So this is, again, the rule for the choice axiom. And if we compare this to the definition, we can pretty much see that it's very similar. So you can win the choice game if you can either win game alpha or if you can win game beta. So this is basically a direct translation. We have proven that this proof calculus is sound and also relatively complete. So relatively complete means that we can prove all valid formulas from all tautologies, if we may assume them in the antecedent. The proof for relative completeness is done in a pretty smart way. So what we did here is to prove those 2 complementarization axioms, that these are admissible. So the complementarization axioms basically express the same as the split we've seen earlier of the winning regions. So we can split any game in DGLSC to 2 adversarial games. So these 2 axioms are admissible, which means they don't alter the strength of our proof calculus. So if we add them, we cannot prove more than before. And with these 2 axioms, we then can again reduce it to DGL and then just use the proof of DGL proof calculus, which is relatively complete already. So we saved a lot of work with that. Okay, now to sum it up, DGLSC is a logic for two players who each have an individual goal and behave semi-competitively. This means that the players cooperate where it's possible for them, but also compete where it's necessary. For this logic, we have developed a syntax and a semantics, and also a sound and relatively complete proof calculus. So with this logic, we can incorporate the goals for all players, and with this additional information, we can prove cases safe that could not be proven safe in adversarial with adversarial assumptions. For future work, we are at the moment working on extending this logic for 3 players. Thank you very much for your attention. Do you have any questions?